Gaussian elimination has three varieties: without pivoting, with partial pivoting, and complete pivoting. Check these examples solved using partial pivoting. Welcome to Numerical Solutions to C Problems. Gaussian elimination is one approach in solving systems of linear equations. This method uses half of the solution by creating a triangular matrix, then computing for the values by algebra. In transforming a matrix, extract the coefficient of each term and arrange them in an augmented matrix. The other Gaussian elimination variation is with partial pivoting. This method looks for a pivot element used to zero out other elements in the column. The pivot element will be equal to 1 to easily eliminate others in the column. The other significant feature of partial pivoting is the interchanging of rows. The problem for the first example is the same system as from Gaussian elimination without pivoting, a system with 4 unknowns and 4 equations. Before starting with the process, we are to look for the pivot element. This is through comparing the x coefficients and taking the dominant element. In this example, it is 4x from row 2. The second row then has to be moved to the first row by interchanging rows 1 and 2. After locating the pivot row to the top, we are to create the pivot element as 1, and this is by dividing the first row by 4, so as to have the first element as 4 upon 4, which is 1. The second element is 1 over 4, or 0.25 in decimals. This is the same with element 3, as also 1/4 or 0.25, and again same with the fourth element, also 0.25. The constant is then 13 over 4, which is 3.25. After fixing the pivot row, we can zero out other elements in the first column. The elements to be eliminated are 3, 2, and 3, using the first row. The second row is then treated with the operation R2 less 3 times R1. The first element is taken as 3 less rise of 1, giving 0. The second element is 4 minus rise of 0.25, giving 3.25. The third is negative 2 less 3 times of 0.25, which yields negative 2.75. The fourth has 1 minus the rise of 0.25, resulting to 0.25. Then the constant consists of 9 less 3 times of 3.25, which gives negative 0.75. The next element to zero out is 2 from the third row. This is done using R3 less twice of R1. The first element then is 2 minus twice of 1, leading to 0. This is followed by negative 1 minus twice of 0.25, which is negative 1.5. The third has 3 less 2 times 0.25, which gives 2.5. Then 2 minus twice of 0.25 is 1.5. The constant is then with 17 less 2 times of 3.25, which results to 10.5. To complete the first column, we also need to zero out 3 from row 4. The row operation is R4 less rise of R1. The first element is then 3 less 3 times of 1, which results to 0. The next element has 2 less rise of 0.25, leaving 1.25. The third element is 1 minus 3 times of 0.25, resulting to 0.25. The fourth then is negative 1 minus 3 times of 0.25, giving negative 1.75. For the constant, there is 6 minus 3 times of 3.25, which yields negative 3.75. After the completion of column 1, we restart the procedure by determining the pivot element to be used for the second column. Since row 1 is already the pivot row for the first column, the choices for pivot element are 3.25, negative 1.5, and 1.25. The biggest value of which is 3.25 from row 2, and this is the perfect location for the pivot element now. Next is to make the pivot element equal to 1, so divide row 2 by 3.25. The first element is then 0 over 3.25, which is 0. The next is 3.25 over 3.25, giving 1. The third element is negative 2.75 over 3.25, yielding negative 0.8462. The fourth is then 0.25 over 3.25, resulting to 0.0769. The last element under the constant column is negative 0.75 over 3.25, giving negative 0.2308. It is best to use fractions for this case, although to create a clearer discussion, decimals are used rounded off to the fourth place. Now we can zero out the other elements from the second column. They are negative 1.5 and 1.25, those below the pivot row. For the third row, we use the operation R3 plus 1.5 of R2. The first element of which is 0 plus 1.5 times 0, giving 0. Next is negative 1.5 plus 1.5 times 1, which is also 0. After this is 2.5 plus 1.5 times negative 0.8462, resulting to 1.2307. The fourth element has 1.5 plus 1.5 of 0.0769, yielding 1.6154. The last is 10.5 plus 1.5 times negative 0.2308, which gives 10.1538. Now let's zero out 1.25 from the fourth row. The operation is then R4 minus 1.25 times R2. The first element is then 0 minus 1.25 of 0, which is still 0. The next is 1.25 less 1.25 of 1, giving 0 again. The third has 0.25 minus 1.25 times negative 0.8462, resulting to 1.3078. The fourth has negative 1.75 minus 1.25 times 0.0769, yielding negative 1.8461. The last contains negative 3.75 minus 1.25 of negative 0.2308, giving negative 3.4615. This completes the second column. We then look for the pivot element for the third column. The choices now come from the third and fourth rows. The dominant value is 1.3078, so we have to interchange rows and place the pivot element to the third row. The third row is then the pivot row for the third column. The pivot element must then be equal to 1, so row 3 should be divided by 1.3078. The first element is 0 over 1.3078, which is 0. The second element is then the same 0. The third element has 1.3078 upon the same to have 1. The fourth is negative 1.8461 over 1.3078, giving negative 1.4116. The last has negative 3.4615 upon 1.3078, which is then negative 2.6468. Checking on the matrix, there is only one element left to complete the triangular matrix down the third column. Eliminate this using row 3 with the operation of R4 less 1.2307 R3. Starting with the first element, having 0 minus 1.2307 of 0, which also gives 0. This is the same with the second element. Then, for the third element, there is 1.2307 less 1.2307 times 1, which then makes it 0, followed by 1.6154 minus 1.2307 times negative 1.4116, which is 3.3527. The last has 10.1538 minus 1.2307 of negative 2.6468, which yields 13.4112. Now that the matrix is triangular, we can work on back substitution to look for the variables x, y, z, and w. From the bottom row, there is 3.3527w as equated to 13.4112, where w is then solved as 4.0001, taken as 4. The third row has z minus 1.4116w as equal to negative 2.648. Place w of 4 and get z minus 1.4116 times 4 as equated to negative 2.648. Isolate z to have negative 2.648 plus 1.4116 by 4 to have z as 2.9984, also simplified as 3. From the second row, y less 0.8462z plus 0.0769w is equated to negative 0.2308. Place w of 4 and z of 3 to have the equation y minus 0.8462 times 3 plus 0.0769 times 4 as equal to negative 0.2308. Isolate y and simplify the terms to have 2.0002 or simply 2. From the first row, x plus 0.25y plus 0.25z plus 0.25w is equal to 3.25. Plug solve values for 2 of y, 3 for z, and 4 for w into the equation to have x plus 0.25 times 2 plus 0.25 times 3 with 0.25 times 4 as equal to 3.25. Transpose all terms to the constant and isolate x to have x equal to 1.